Let's prove this identity, that secant theta minus cosine theta is equal to sine theta times tangent of theta. I think my approach will be to take the left side and make it look like the right side. To start with, so I'll copy down the left side, secant theta minus cosine of theta. How can I start working with this? I can't do much with cosine, but secant by definition is 1 over cosine, so let's replace it with that. So secant of theta is 1 over cosine of theta, and we're subtracting cosine of theta. So again, still just working with the left side, making it look like the right side. I think what we could do next is subtract these two terms by getting a common denominator. That common denominator is going to be cosine of theta. So over here, I'm going to multiply the top and bottom by cosine of theta over cosine of theta. That will give me a common denominator of cosine of theta. And in the numerator, we have cosine squared theta. So I'll continue that work over here. But this is 1 minus cosine of theta minus cosine squared of theta over cosine of theta. With this common denominator, I can now subtract the numerators. That is, this is equal to 1 minus cosine squared theta over cosine of theta. And now what? Well, I'm seeing this 1 and a cosine squared theta. I'm going to reference an identity, a very important one of the Pythagorean identities. Sine squared of theta plus cosine squared of theta is equal to 1. If I subtract cosine squared from both sides of this identity, sine squared of theta is equal to 1 minus cosine squared theta. So this is a very powerful identity, and it often shows up when working with proving identities. That all being said, this is 1 minus cosine squared of theta. I'll replace it with something simpler, sine squared of theta. So we have sine squared of theta over cosine of theta. And our target is to get to here, and we're getting kind of close. Well, over here I see two things being multiplied together. Maybe I can split the numerator up so it's not sine squared, but I'll write it as sine of theta times sine of theta. That's the same thing. We can either divide this whole thing by cosine of theta, but since it's a product, we can just divide the second piece by cosine of theta. And now this is starting to look a lot like this. I have the sine of theta, I just need tangent, and by definition, sine over cosine is tangent. So that is, we have sine of theta times tangent of theta. This proves the identity. The method being, pick a side, simplify it until you get to the other side of your identity, and you can use this as a guide. You want to make it look like this so you can start breaking things apart and using identities to get there. I do think it's also possible to reverse this. You could have picked this side and made it look like the left side. That would have been totally fine, but that is it for this problem. Let's compute the exact value of cosine of 3 pi over 2 plus 2 pi over 3. And we're going to use the sum difference formula for cosine. So maybe I'll state that formula first. The formula is, if you have cosine, and actually since we have addition here, I'll just focus on the sum version. So cosine of two angles being added together is equal to cosine of angle A times cosine of angle B minus the sign changes, and then we have sine of angle A and sine of angle B. So here A is equal to 3 pi over 2, and B is equal to 2 pi over 3. What I will do is directly plug this information into this side of the identity. We have the following. We get cosine of 3 pi over 2 times cosine of 2 pi over 3 minus sine of 3 pi over 2 times sine of 2 pi over 3. We have to now figure out the exact values for these four trig functions. I'm going to reference a unit circle as a guide. For starters, where is 3 pi over 2? If you start here at 0 and count by pi over 2's, 1 pi over 2, 2 pi over 2, 3 pi over 2. So this is 3 pi over 2. On the unit circle, the coordinates of that point are 0, -1. The x value is 0, the y value is -1. But by definition, cosine is the x value and sine is the y value. So this thing here is equal to 0, and this thing here is equal to -1. That's actually nice that this thing is equal to 0 because, well, whatever cosine of 2 pi over 3 is, it really doesn't matter. When I take the product of that with 0, it completely cancels. So let's actually do that. My next step is, okay, so maybe I'll make note of it, that this thing here, this is 0. And 0 times anything is going to be 0. Again, coming from the x coordinate at this angle. I'm going to pick up here. I have minus, okay, sine of 3 pi over 2 is -1. And now I just need to know, well, what is sine of 2 pi over 3? Whatever that is equal to, I'll put here, and I'll multiply all of this stuff together. So 2 pi over 3, where is that? 2 pi over 3 is here. Again, counting by pi over 3s, you'd have 1 pi over 3, 2 pi over 3. So we need to figure out what is the exact value of sine of 2 pi over 3. As a reference angle, we get pi over 3. That means that sine of 2 pi over 3 is either equal to sine of pi over 3 or it's equal to the negative of sine of pi over 3. Since sine is positive in the second quadrant, this is equal to sine of pi over 3. And sine of pi over 3 is equal to the square root of 3 over 2. So that's the value I put here. So negative times -1 times root 3 over 2 simplifies to positive root 3 over 2. And that is the answer to this problem. Let's use this triangle to figure out the exact value of cosine of 2 alpha. To note here, we have a right triangle, so I'm just going to put this right angle in here. And this angle is alpha, yet this one is 2 alpha. We must use the double angle formula for cosine in this problem. And there's a few versions of it. I'll list them all. Cosine of 2 alpha, that's equal to cosine squared alpha minus sine squared alpha. It's also equal to 2 cosine squared alpha minus 1, and also 1 minus 2 sine squared alpha. So all of those things, we can use any one of them that we want to get our answer. If you want to use any of these formulas, well, you first have to know what cosine of alpha is or what sine of alpha is, and that we can figure out from this triangle. So for example, if you want to know cosine of alpha, that's the adjacent over the hypotenuse. If you want to know sine of this, it's the opposite over the hypotenuse. Basically what I'm saying is, well, we need to know the hypotenuse, which is c. And I'm going to use the Pythagorean theorem to figure that out. 7 squared plus 24 squared is equal to c squared. So I'll simplify this in my calculator. 7 squared plus 24 squared. That is 625. And if we want to solve for c, which is a positive value, we get 25. So that's c. This means we now know two things. Sine of alpha is the opposite over the hypotenuse. That's 7 over 25. And cosine is equal to the adjacent, so cosine of alpha, the adjacent over the hypotenuse, 24 over 25. So I really think probably, let's see, I'm going to go with this one here. I'm going to use this version just because it has one trig function in it. We have that cosine of 2 alpha is equal to, okay, it's 2. I come across cosine squared alpha. I'm going to put 24 over 25 in place of the cosine alpha, and we're going to square it. Then we will subtract 1. To get our answer, all we have to do is just simplify this. Square this out, put it into one fraction. Okay, so 24 over 25 squared. Some large values here, but this is 2 times 576 divided by 625. I'll write 1 as 625 over 625 to get a common denominator, and I'll take this 2 and multiply it to this numerator. So 576 times 2, we get 1,152 divided by 625, and we're subtracting 1, which is the same thing as subtracting 625 over 625. We have a common denominator. I now can just subtract the numerators. So that's 1,152 minus 625. That is 527 over 625. I don't think there's any common factors between the numerator and the denominator. So this fraction, this value right here, is the exact value of cosine of 2 alpha. So again, here it was only alpha. So we had to do a little bit more work by using one of these identities to get this final answer.